So this is going to be a video on Chapter 10.2, which is about linear correlation, how to identify it, and how to interpret it. So what is a correlation? So a correlation is when two variables are related to each other. It does not mean causation. So it does not mean that one variable causes the other to behave in a certain way. It simply means that they kind of go up and down in a certain, similar pattern, so to speak. So it means that they're, again, related, not that they're causal. So again, correlation does not mean causation, as the old stats saying goes. So R is the linear correlation coefficient. So it tests the strength of a linear relationship between x and y. So you have, a bunch of data for x. Maybe you're tracking the age of people, and then you're tracking y, which is the height of people. We'd expect that the age and the height have somewhat of a high linear correlation because as you grow older, you also grow taller, typically speaking, up to a certain point at least. So again, that's what x and y are. X and y are different things you're measuring, and you're comparing to see how good of a linear relationship that they have. So these are some cases that could happen. So you could have a strong positive linear correlation, which means you're going up in sort of a linear fashion, or a strong negative, which means you're going down in a linear fashion. So a strong positive means as x goes up, y also goes up. That's what a positive linear correlation is. A negative linear correlation is the opposite. A negative linear correlation means as x goes up, then y goes down. Or again, vice versa. As y goes up, x goes down. So a negative correlation means that they go up and down in opposites, whereas a positive correlation means they go up and down together. Whoops. My bad. Then you have moderate and moderate. So again, moderate means that there's not quite as strong a linear fashion to it, but still goes up and down. And then you have, no correlation. No correlation means that there's no going up or down. It's just kind of a spread out scatter plot. And a curved linear relationship means that it has a sort of a negative linear relationship, and then at some point in time, because of something changing or whatever, now it has a positive linear relationship. So it kind of has both a positive and a negative linear relationship at different points in times. And then, okay, what makes it strong versus weak? Well, it all depends on how close you are to 1 or negative 1. So if you find R, and we'll talk about how to find R in a second, if it's 0, that means there's no correlation. So this is kind of where R is 0. Okay? But if it's closer to 1, that means it's a stronger positive correlation. If it's closer to negative 1, that means it's a stronger weak negative correlation. So strong positive, you're close to 1. Strong negative, you're close to negative 1. And again, what defines as, qualifying as we can statistically say this is a linear relationship? We'll talk about that later in the video here in a minute. But for right now, we can just think about it as kind of gauging how close it is to 1 and negative 1. Close to 1, strong positive. Close to negative 1, strong negative. If it's just like negative 0.002, that's close to no correlation, or maybe you can say a very, very weak negative correlation. So again, right now it's kind of up to our discretion, but we'll talk about the cutoffs here in a second. So what are the requirements to running this test? Well, you have to have a pair of data, x and y. It has to be a random, independent, quantitative data. Quantitative means that it can be put into number form. So you're not tracking, eye color. You can't really do this with that. Visual examination of scatter plot must confirm that the points approximate a straight line. So again, you have to kind of, the second one there's kind of an iffy thing there, because if it doesn't approximate a straight line, then the R is likely going to be 0 anyway. But if you have a scatter plot and you can see, hey, maybe there's something here, and that they should kind of show a straight line before you run this test here. And then any outliers must be removed if they are known to be errors. So again, if you're measuring data and you have 100 data points, and you know that one of them is really, really, really far out there from the rest, that could be that one was gotten an error, and you might want to drop that one because that could throw off the entire calculation. So any outliers you want to nix first before you run this test. And so, what are some notations we're going to need to know? So n is the number of data present. So I should say that n is the number of data pairs that are present. Not the data points, but the data pairs. So, if I have 5 x's and 5 y's, my n is 5, because there's 5 pairs of data. Sigma x is the sum of all x values. Sigma x squared means that you should take each x value, you should square it, and then you take the sum of those. So you square it and then sum them. This is slightly different. This means that you square the sum of the values, which meant saying, okay, well, isn't that what you just said? And no, it's not. This means that you're going to add all the x's first and then square that result afterwards. So the second one is the backwards version of the first. This one here, you square and then add. This one down here, you add and then square. That's why the parentheses is there. So add, then square, versus this one, which is square, then add. Then add. So sum of xy means you're going to take the sum of all the x values multiplied by all the y values. So again, this means that you multiply all the x and y's together first, and then you add them up together. And then r is what you're looking for. This p here is the Greek letter rho, I believe. So rho is how it's spelled in the English vernacular. And that's just representing the linear correlation coefficient for the population. So it's kind of like, saying mu. Mu is the average of the population. X bar is the average of the sample. R is kind of like our X bar. Rho is kind of like our mu. Right? So what is this all used for? Well, to get the R, we're going to do this, which is a very simple, easy to follow, understandable formula, right? So you multiply the x and y's together, then you add them up, then you multiply by the number of pairs, and you subtract that by the sum of all the x's and the sum of all the y's after you are first, and then you multiply those together. So here, you multiply all the x's first, you multiply all the y's, or sorry, said it backwards. You add all the x's first, you add all the y's first, and then you multiply them together. And then on the bottom, you take the square root of basically kind of what you did up here. You take the n value times, well, you get the idea, right? So it's a pretty simple, easy to understand formula that we can use to apply this. So let's go ahead and do it here. So we have all this data here, and so we need to find all these numbers here, and I'm not really going to make you do that. So obviously, because this calculation is kind of long and involved, there is a way we can do this on the calculator. Now, there is a little bit of setup you have to do first. Now, I have mine pre-set up for this, but I'm going to show you how to do it on yours. You're going to go to second, and then down here above the 0, there should be a little yellow button that says catalog. You're going to hit that, and then you're going to want to go all the way down to where it says diagnostics on. You can scroll down if you want to, just kind of scroll down, or you see how it's kind of set to alpha mode here. Above the keys, there should be greenish numbers, or depending on what calculator you have, it might be blue or blackish numbers. Right here above the x -1, there's a little green D. If you click that, it should bring you automatically down to the start of the D column. So this is the start of the, right here, this is the start of the D column. And if you go all the way down, diagnostics on is not too far away. So you go to diagnostics on, you click enter, and you're done, and you're good. Unless you reset the memory, you shouldn't ever have to do that again for what we're doing here. Right? Your calculator is already set to be in stats mode now. So what you're going to do is you're going to enter your data into L1 and L2, our good old friends L1 and L2. You're going to calculate using the linear regression feature in your stat menu. And then once you've ran it, you'll see both r and r squared. And we'll talk about r squared means here in a second. So let's go ahead and do that on this data here rather than doing it by hand, yes? So stat, calculate, edit. Enter our list first. I already have them pre-entered. That's why I kind of skipped that step. So you enter your duration in column X, or list 1. You enter your intervals in column Y, or list 2. So I did this as my L1. This is my L2. It actually does not matter which one you put in as L1 and L2. Your R will be the same. So again, it doesn't really matter. And then, as I said, once you got that down, you're going to go to stat, calculate, not test. We're finally get out of that test thing there, right? Linear regression. So linreg, click enter, and boom, gives you r squared and r. So in this case, my r is 0.9255, so we'll put 926. So r in this case is 0.926, which is pretty darn close to 1, right? So we can say that this probably has a pretty strong positive correlation because of the fact that, again, it has an r of close to 1. Now again, is it strong enough to say that there is a correlation, statistically speaking? Well, we'll get that in a second. But right now, we can just say that there looks to be a strong positive correlation based on this data set here. So what are some properties about R? So remember, R has to be between -1 and +1. It can't be lower than -1, can't be higher than +1. As I just said, it's not affected by what you choose as your L1 and L2, or in math term, your X and your Y, right? You can choose anyone to be your X, anyone to be your Y. All you're testing for is there a correlation? So it doesn't matter which one you put first, you're going to just be testing the same two things anyway. And then remember, R measures the strength of linear correlation. Let me say that again. R is used to measure the strength of a linear relationship. It's not used to measure the strength of something that's not linear. So we have stuff for that. We have a quadratic linear regression. We have an exponential linear regression. We have a bunch of different linear regression, or sorry, I shouldn't say linear regression because that makes no sense. We have an exponential regression, and we have a quadratic regression test that we can do. R is specifically for linear relations, right? So unless it's linear, it's probably not going to give you a good R, right? Probably going to be closer to 0. So what is this r squared then? So r squared formally is called the proportion. Proportion of the variation in x or in y that is explained by the linear relationship between x and y, which sounds confusing because it is. So let me see if I can't break that down a little bit. Let's say we have an r squared of 60% for something. That is something that's called the explained variation. So it means that 60% of the data fits a linear model. Now, again, that sounds confusing here, so let me try to listen to that one more time here. R squared represents what percent of the relationship can be explained by this variation. That means, again, this is kind of a weird concept, so I'm trying to kind of going through as much as I can here. That means that you can kind of, this is a very odd way of saying it, and it's not quite right. But again, for an intro-level stat course, if this kind of gets it in your memory so that you can kind of work with it a little bit right now, we can formalize the idea later if you decide to go into this further. But right now, you can think about r squared as what percent of the relationship here is caused by this correlation. So again, for the, actually I can pull it up my calculator, right? I think it's still saved there. Yeah. So r squared is 0.86, we'll say, 86%. So we can say that 86% of the relationship between the duration of Old Faithfuls, I should have probably introduced that sooner, shouldn't I, instead of just going through the data here. So remember, we were testing to see what the correlation was between the duration of Old Faithful's activation and how long it takes to activate again, right? So, it went on for 240, I think it's minutes here, and then it was dormant for 92 minutes, and then went on for 120 minutes, and then it was dormant for 65 minutes. So what's the relationship here? We found that it had a linear correlation. So our r squared means that 86% of this, 86% of the reason for this duration here can be explained by the linear relation between the duration and the interval after. So again, you can kind of think about it as the duration after the duration before Old Faithful bursts again. So these numbers down here, the duration that it takes to burst again, 86% of that is caused by the duration of the actual eruption that came before it. So 240 led to a 92-minute dormancy. 86% of that reason was because it went on for 240 minutes beforehand, which means that 14% of it is caused by maybe other factors. Maybe it's caused by water pressure. Maybe it's caused by location. Maybe it's caused by air temperature. I'm not sure what goes into the geology of it. But think of r squared, again, for right now, even though it's not quite accurate, think of r squared as what percent of this result is caused by this linear relationship here. So 86% of how long it takes to erupt again is caused by the duration of what it did before. And 14%, therefore, the other half, not the other half, but the other part of it, is caused by other factors. So we'll go into another example of that too, because again, r squared is a very difficult concept to get right away, and nor should you, because it's a very difficult concept anyway. Now, let's focus back on r here for a minute. So how do we actually figure out what r is what we're looking for? Well, how do we figure out what r makes for a statistically linear correlated set of data? Well, you're going to take the absolute value of the r, because remember, r can be negative. Just taking the absolute value makes it easier to compare. And you're going to refer to table A6, and we're going to conclude that there is a linear relationship if the absolute value of r exceeds the value in the table A6, which is, right, I thought I had it up here. There we go, right here. So n, remember, is your data set. So this is the number of pairs of data that you have. If you don't have the exact number of pairs, you pick the closest one. So this says that if you have 4 data sets and you're doing a 0.05 significance test, because this is kind of like a significance test. So if you want to be 95% confident in your answer and you have 4 data pairs, then you're looking for 0.95. If you're above 0.95 for your r, then you can say that there is a linear correlation. If you're below 0.95 for your r, then you can't say there's a linear correlation, at least not with 95% certainty. If you want to be 99% certain, then you have to have a correlation of 0.999 or more, which is, again, is very strict. Because as you can see here, the lower your n, the higher your correlation has to be for both columns. Because it makes sense. If you have 100 pairs of data, and you can see already that there's some sort of linear relationship, you don't really need that much evidence to further prove your point. You have 100 pairs of data that show that, okay, as one goes up, the other goes up. I mean, there's 100 pairs of data showing this here. So you don't really need that high of an R. But if you only have, 7 pairs of data, well, then maybe you need a little bit more of a stronger correlation for just those 7 pairs if you want to be certain that there is a linear correlation here. So if it's above this value here, this is what we call the critical value. If it's above the critical value, then hey, there is a linear correlation. Otherwise, there is not evidence to show that there is a linear correlation. Again, it's kind of like failing to reject or rejecting in terms of hypothesis testing. So let's take a look at this here. 8 killer grizzly bears were I can't say that word. 8 killer grizzly bears were kills or sleeped. Researchers took the measure of their chests and then weighed the bears, and the value of this correlation was 0.993. So we had 8 bears measured and weighed. We compared the weights of the bears to the size of their chests, and we found that the linear relationship was 0.993. If we want to be 95% confident in our assertion, so 0.05, is there a linear correlation between chest size and weight, and what proportion of the variation can be explained? So is there a linear correlation between chest size and weight? Well, let's see. If we have 8 grizzly bears, that means we have 8 pairs of data. Our R was 0.993. We want to be 95% certain. So 95% certain, 8 pairs of data, 0.707. Well, 0.993, 3, is definitely bigger than 0.707, right? So it definitely passes the linear correlation test there. So we could say with 95% certainty, with 95% degree of accuracy, that yes, there is a linear correlation because our R is above our critical value. Now, this plus part here says what proportion of the variation can be explained by the difference between weight and chest size. So if I plug that in here, remember, this is when they ask what proportion, this is the R squared business. So if I take 0.993, and I square it, I get 0.986. 0.986, which translates to 98.6%. So what is this 98.6% telling me? Well, it's telling me that the 98.6% of the bear's weight can be predicted or explained by the size of his chest, and vice versa. Which makes sense. The bigger the bear, the wider the chest is, right? That means that's how bears grow. So that's what I'm trying to get at what R squared means, is that 98.6% of the cause of the bear's weight is determined by the size of their chest. Now again, that means that 1.4% of the weight is determined by other factors. Maybe it could be, once again, gender, location, age. Those could be other factors that determine their weight. Well, those are other factors that determine their weight. But this says that 98.6% of the relationship between weight and chest, are 98.6% of the variation in weight, I should say, the variation in weight, can be explained by the size of the bear's chest. So if I have 2 bears and they have different weights, and you ask yourself, well, why do these 2 bears have different weights? Well, 98%, we'll just say 97 here because it's going to get tiresome saying that. 97% of the, rounding, that'd be 99%. So 99% of the difference in weight can be explained by the fact that those 2 bears have different chest sizes. So why do 2 bears, same age, same location, they have different chest sizes and different weights? So why do they have different weights? Well, 99% of the reason is because they have different chest sizes. Okay? That's what this is kind of saying there. Again, not necessarily the most accurate description, but it's like, not to keep using percentages here, that's like a 90% description that you can work with. About 10% of that is a little bit iffy, but 90% of thinking it that way is going to get you there. Okay? Again, that's good enough right now for an intro to this topic here. So hypothesis test for correlation. Again, we do have a hypothesis test here. We can use the test statistic, which is, again, the t-score that we have there. Shows you the formula for that. You can use the table A3 like we do for our t-values. Or, like I said, we can just do what we just did, which is what we're probably going to be doing here, and running the test statistic for R. So, again, we don't really need to use this too often, if at all. I might put it on there as like a bonus question, run the test statistic t-score for this. But as far as for me personally, I'm not going to have you do the first method too often, just because, again, the other methods get more easily accessible and it kind of relates more. And we've done t-test too much right now, right? And again, method 2 you can do in your calculator. So that's always a bonus. All right. So test the claim that there's a linear correlation between the duration and the time interval after the eruption. So this is the same set of data. We're going to use a 99% significance test here. So let's just go back to the data we had, because we already should have this uploaded in our calculator already. So if we run this again, just because I don't remember the exact numbers here. So in our case, we had an R of 0.926. So our R here is 0.926. So is that enough to say that there's a linear correlation with 99% certainty? Well, let's see here. We have, I forgot to tell us here, we have how many pairs? 1, 2, 3, 4, 5, 6, 7, 8 pairs of data again. So 8 pairs of data, we want to be 99% certain. which means we're aiming for a 0.834 or more. We definitely have that. So this is definitely bigger than 0.834. So in this case, we'd say, yes, there is evidence for a linear correlation, right? There is evidence that these two things are linear correlated. As one goes up, the other is going to go up. As one goes down, the other goes down. And again, it makes sense. If you think about how the geyser works, there's a store of water that bursts up. Well, if it lasts longer when it's bursting, it's probably going to take longer to refill the next time. But if it doesn't burst as long, it's probably going to have more water left over, so it's going to take less time to burst again. That's probably why it's such a strong correlation, because that's probably one of the main causes of how long it takes to burst again. So why does it take different times to burst each time? Well, once again, if we look at the R squared, we can say that 86% of the reason that there's different time intervals in terms of when it bursts again, the 86% of the reason that between bursts is not consistent is explained by the duration of the eruptions. The fact that the durations aren't consistent, aren't 100% the same, 98%, or that can explain the difference in the interval eruptions. Right? So again, in this case, there is enough evidence, pretty strong evidence too, that there is a linear correlation. So what about some other ones here? So these are budgets and total grossing after randomly selected movies, and we want to figure out, is there a linear correlation? And it says, apart from the budget amount, identify one other important factor that might lead to the amount of money a movie earns. Okay, so we want to figure out, if you spend more money on a movie, is that linearly correlated with how much that movie will make? Remember, budget is how much you're going to spend on the movie, gross is how much it's going to make. So let's enter these numbers in here. So 62, we're assuming these are billions in dollars here, or millions at least, because we probably don't spend 62 bucks on a movie. We probably spend 62 million on a movie, would be my guess. So 62 million, 90 million, 50 million, 35 million, 200 million. It's probably a Marvel movie there, right? 100 million, and 90 million. I'll delete the rest of my list here. And then over here, remember, these are pairs of data, so L1 and L2 should have the same amount of numbers in them, because these are pairs. This is kind of like a matched pair thing. 65 million, 64 million, which is really odd for a 90 million movie to only gross 64 million, right? Less than the 62 million movie. But again, that happens, right? Not every time you spend a bunch of money on a movie is it going to make a bunch of money back. 50 million, oh, sorry, 48. I was looking at the wrong list there. 48 million, 57 million. So that's a low budget film that made quite a bit. 601 million, again, Marvel film. 146 and 47. Okay. So again, you have, high spending, high earning. Again, like I said, Marvel film. And then you have, high spending, low earning by proportion, probably a DC film. Just a joke there. Don't hate on me. I really don't have a preference one way or another. Just making a joke. Anyway, let's go to calculate the linear regression here. Okay. Boom, boom. All right, so our R, kind of like Old Faithful here, actually. Make sure I still enter those, because that's actually almost exactly like the Old Faithful. Let me make sure my stats are actually entered in. Make sure I don't have any lingering numbers there. Okay, well, we're good. That was just coincidence, I guess, that it's almost exactly the same. Yeah, okay. So we have about, once again, 92 or 0.926. So 0.926, which is, yeah, almost exactly the same as we had the last time. So 0.926 of our stuff can be explained by, or is our R. So with a 95% certainty, is that enough? Well, let's see here. We have 1, 2, 3, 4, 5, 6, 7 this time. So we want to be 95% certain with 7 pairs of data. So 7 pairs of data, 95% certain. We're looking for 0.754 or more. Well, again, that's definitely bigger than 0.754 or more. So 754 or more. So in this case, yes, there is a linear relation between how much you spend on a movie and how much it's going to make. So that means, typically speaking, the more you spend, the more the movie is going to make. And again, makes sense, because the more you spend, the more you put into the movie, the more it's going to make, obviously. So let's go ahead and see what the R squared is. The R squared, just like before, because it's the same number, is 0.86, right? So 0.86 is our R squared. So we can say that 86% of the reason, again, this is not super accurate, but it's close enough. 86% of the reason that movies make different amounts of money is because they spend different amounts of money making the movies. 86% of this variation here, the reason that this movie made so much more than this movie, made so much more than this movie, than this movie, than this movie, 86% of that reason can be explained by the fact that they spent more money than the others. Right? Now, the other part here is, okay, apart from that, what's part of that other 14%? Right? Because if 86% can be explained by the fact that they paid more money, okay, fine. But what's that other 14% there? That's what we call the lurking variable, is the part that you're not studying that also plays a role here. Because you're just focusing on budget and gross. You're not focusing on other variables that could have an impact here. Which now, you're focusing on the largest chunk, it seems. But what are some other variables that might happen? So in this case, you go to things like, okay, well, actors, right? If you get a very well-known actor, even if you don't spend that much money on it, then again, you can really make some money with that. If you have something like the quality of the movie, if it's just of high quality because you have good technique and you know how to direct and it's a good story, whatnot, that could also explain why some movies make more than others. You could have the type of movie. So maybe people where you're releasing the movie have a bigger preference for action movies or whatever. So the type of movie can affect how well it's going to do. Maybe not everybody in the world likes rom-coms. So if you're doing a rom-com movie, maybe you're not going to make as much money even if you spend more than an action movie who's going to make much more than you but spending less. So 14% of the variation here can be explained by, again, stuff like the actors featured, the type of movie, the quality of directing and story and whatnot. But 86% of it can be explained by how much money you spend on it, which is a large chunk, which means that, if you're going to make a movie, you're definitely going to want to invest a lot of money into it because that's going to be the largest driving force so far that we can see here versus the other stuff. So once again, if you want to scatter plot this here, I think I did scatter plots really early on in the semester, but I'm going to tell you again here how to do this because once more, one of the ways that you can look at this here is to just make your own scatter plot. So we have our data in L1 and L2. We go to second y equals, which brings up the stat plot. We're going to go to plot 1. We're going to set it to on, and we're going to make sure that the first type is selected right there. Make sure that our two lists are entered in correctly. Again, it doesn't really matter which one's which, but we're going to make sure our lists are entered correctly. You can pick which type of graphical display you want. It really doesn't matter. I recommend not doing this because, at least for me, it's hard to see. But any one of these other two would work well. But if you're really keen eyesight, then maybe you do that one. I don't know. But then you're going to go to clear, and then you're going to go to zoom, and you're going to go to zoom stat. This will zoom in or zoom the stat plot on your screen. And we can see how the scatter plot looks. So this is my data plotted. Now again, you can see that large that's our Marvel movie right there, right? High spending, high earning. That's that Marvel movie, and the other movies are kind of down here. And you can see that there is kind of a positive relationship going on there. This we consider more of an outlier, no? Now it was probably accurately gathered, but it looks like it's an outlier compared to the other ones here. Now, if we had more than just 7 movies, maybe we'll fill in this gap a little bit, and it wouldn't be such an outlier. But in terms of these 4, that one's definitely an outlier. But even still, you can see that it's kind of a positive correlation here as it's rising up there. But as always, and this is true for everything, the more data you gather, the more accurate result you're going to get. So we just did 7 movies. If we did 700, this would probably be filled in a lot nicer, and we can see that the graph is definitely a positive correlation there. Okay. So that's the homework that may or may not be there. Again, I'm not sure when this is going to air and what changes I'm going to make, but make of that what you will. But for right now, this is going to end the video here. Like I said, don't bother. I know it was kind of cruel of me, but you don't have to. Let me get back here. There we go. So you don't have to use that nasty little formula right there. That is all going to be done in your calculator. You're going to pawn that off to your calculator, tried and true, so you can focus on the important stuff, which is interpreting the results and communicating. Because that's what stats is. Stats is not just running a bunch of formulas. That's what we do, but not what it is. Stats is taking those answers from those formulas and interpreting what they mean. And that's where we spend our time here, especially second semester, as you hopefully have noticed, on interpreting these numbers rather than gathering. So first semester was kind of, okay, how do we gather these numbers? Kind of the basis of, what is an average and what does it say and how can we use it? Because if you notice, we've been using a lot of averages in our stuff here. Throughout the second semester in general, at least. And so on. So we gotten how can we get these sort of basic stats calculation-wise? And second semester has been all about, okay, now that we can get these basic numbers, what are some overall concepts we can get, like R here, and how can we interpret those in a meaningful way, right? So that's my little rant there. Hopefully you enjoyed the video. Hopefully it helped you out. Let me know if you have any questions. Have a good day, night, or whenever you're watching this.